CUET from the Department of Physics, University of Chicago. This is actually my first official presentation in such a setting, so I'm quite excited. First of all, I'd like to mention my title, which is exactly Generalized State Discrimination for Binary Non-orthogonal States. And we'll talk about this thing in later slides, but what you need to know is what we did was generalize a process called state discrimination, and we did that for two non-orthogonal states. First of all, what is a quantum state? In quantum mechanics, we always say quantum states are the basic objects that have all the information about a quantum system encoded in them. In the matrix mechanics, we say, however, in matrix mechanics, we say that the psi here, the quantum state here, can be represented as a column vector, or specifically a column matrix. And I won't exactly mention them much in the later sections, but what you need to know is that it is basically in a superposition state of two computational basis states. The 0-ket and the 1-ket are respected on our Rafik sir always mentioned. So here we can see in this picture that this particular quantum state has projections on 0-ket state and 1-ket state, right? So if we want to measure something, what it means to measure a quantum state is actually to take the projection of that state on our computational basis. What it does is, when we take measurement or the projection, we could find 0 or 1. It doesn't exactly tell us enough information to find out what our state psi was. So we would have to take about 1,000 or 10,000, as many as counts we could, to find out exactly what the state psi was by finding out what alpha and beta are from the probabilities. So this is the basic idea of what a quantum state is in this regard. Let's come to our problem. So we want to do quantum state discrimination. What it means is we want to distinguish between two known quantum states. We have our sender and receiver. Our sender is called Alice and receiver is Bob. Alice is going to send one of two known quantum states to Bob. What Bob needs to do is find out exactly which state Alice has sent him. So how can we do that, and can we even do that? In the first case, we consider the two states psi1 and psi2, and these are basically in the direction of the computational basis. Why is it significant? First of all, we have seen here there is this angle which is called theta, right? So what it is the overlapping angle between the states. And in the Hilbert space, if the angle between them is pi by 2, we call them as orthogonal states. And basically what it means is psi1's projection cannot ever end up on the end of psi2. So basically if we find 0 upon measurement or projective measurement, we can basically say that it came from psi1 state. So Bob can conclusively detect psi1 or psi2 depending on what Alice has sent him. So in this case, yes, we can do that. We can distinguish between these states. However, when we consider psi1 and psi2 like this, so here the overlapping angle isn't exactly 90 degrees, right? So in this case, let's say we did a projective measurement and found 1. What it means is we have found a projection of psi2 in this direction, because it's not exactly possible for psi1 to project itself on this basis, right? However, when we get 0, what does this mean? This actually can mean two things, because psi1 also has projection in this direction, psi2 also does the same. So this means we cannot exactly conclusively detect psi1 or psi2 in this setting. So no, this is not possible. What we can do, however, is to find out how we can do that, because we're not exactly in the new territory here, right? So somebody must have done something. And we found this problem quite fundamental to quantum computing and quantum key distribution, because finding out which state we are working with is quite a basic concept. So our research question was quite simple. How can we better discriminate between non-orthogonal quantum states? So what we did was find out what the existing strategies were. We found an approach called Hellstrom, another called IDP, and also called FRIO. The Hellstrom and IDP approaches where extreme cases where where in the Hellstrom case we wanted to find conclusive detections always. However, in the IDP regime, they performed better and in the accuracy section. So their data was highly accurate when they did get meaningful data. However, most of the time they are getting inconclusive outcomes. FRIO, or the fixed rate of inconclusive outcome, they were a cost-dependent flexibility in the regime. However, they only dependent on the inconclusive results. What we needed was to find a tunable approach that could balance between the two extreme methods and also incorporate the FRIO strategy. So first of all, let me talk a little bit about what the Hellstrom approach does. So we have seen what a projective measurement is. So basically, the Psi1 and Psi2 states are the signal states here, which are being sent by Alice. And for discriminating between them, we have the basis states here. The Pi1 projector and the Pi2 projectors are basically in these directions. So we have seen some kind of symmetry between this, right? These angles being the same. And what I want you to notice is the angle between Psi1 and Psi2, although referred as theta before, in this slide we are calling it 2 theta. So what's the reason? The reason being, the angles in the block sphere are twice of their Hilbert counterparts. And in this picture, we are seeing the block sphere representation of these states. And I want you to remember that as we go along in the new slides. So what in this case is projective measurements, and after that we have the IDP approach where there are 3 basis states, and for 3 basis states there are one which could control the inconclusive outcomes. And this is quite good for us because this gave us highly accurate data, although less meaningful data. What we did was tier this basis in certain way so that we could strategize a trade-off between accurate results and meaningful data. So we found 3 types of data, and these were correct, incorrect, and inconclusive data. And we call them like PS, PE, and PQ because these were actually probabilities, right? When we do counts, we cannot exactly say within a single measurement what it means. But after being measured for several times, we can find out a probability for them. So after that, we saw, let me just explain this one. So we saw that all of these probabilities actually only depend on the tilting angle phi we took. This is our geometrical parameter. So this was the simulation setup. Yeah, so this was the result. We found that the probabilities interpolated between the 2 extremes also incorporated the FRIO strategies, and the 2 significant points of this were the confidence threshold point and physical risk point, where we found some kind of balance in the trade-offs. So we found this for an ideal simulator of quantum computer, where we could find out the Hellstrom limit, IDP limit, also the 2 intermediate regions, ERP and CTP points. So to summarize, this is the table that quantitatively summarizes our slides, and we could infer that by adjusting the measurement parameters, we can optimize the trade-off between accuracy and efficiency based on our requirements.
Thank you so much.